This is lecture number 38 in the FOA series of lectures on fiber optics and cabling. In this lecture, we'll be talking about cabling for data centers. Data centers are facilities where data is stored for access on the internet. Data centers can be enormous, like this Google data center, or the ones operated by Amazon, Netflix, and quite a few others, including NSA. Data centers can also be small, what we used to call computer rooms, like this facility at the new San Diego Central Library, that also is the center of their new optical LAN based on fiber to the home technology. A data center is a building or a portion of a building whose primary function is to house a computer room and its support areas. The main functions of a data center are to centralize and consolidate information technology resources, house network operations, facilitate e-business, and to provide uninterrupted service to data processing operations. Yes, it's what we used to call the computer room before it grew so big it filled buildings. Data centers can be part of an enterprise network, a commercial venture that offers host services for others, or a co-location facility where users can place their own equipment and connect to the service providers over the building's connections. The data center is comprised of switches connecting users to servers and more switches connecting servers to storage. It sort of sits in between the LAN, the private local area network, and the WAN, the internet. This is probably a good point to say that data centers follow typical high technology linguistics. That is, it has its own language and many TLAs. TLA is a three-letter acronym. Sometimes the language and the TLAs vary from vendor to vendor. We try to avoid this kind of language by using plain English or explaining when multiple terms may be used for the same function. Because of the number of servers typical in a data center, a tiered architecture of switches is used. Access switches connect groups of servers, and interconnection switches connect the access switches. Some architectures have added a third level of switches called core switches, but since that adds complexity, cost, and latency, plus uses more power and generates more heat, a more streamlined architecture is being used in many data centers. Different vendors or groups have different names for some of these components. This switch design is sometimes called fat tree or spine leaf. Interconnection switches are also called aggregation switches and may be called core switches in some cases. Access switches may also be called edge switches. It's all very confusing. Here we're looking at the network architecture that includes the storage area network connecting storage to servers. When you consider the number of units connected and the multiple connections often used for redundancy to ensure reliability, you can see the amount of cabling that a data center can include. Mesh switching links allow servers to more easily use virtualization, where one switch can provide services to more storage with lower cost and power usage. Data centers can have lots of connections. Sometimes they grow organically, and the backside of the racks begin to look like this. Good luck troubleshooting this system. Data centers generally use Ethernet, although fiber channel has been used for storage area networks. However, the trend is now to carry fiber channel over Ethernet to simplify the overall data center networks. Lots of choices are available on data center media. Classic UTP cable, Coax, Multimode or Singlemode fiber, and even active optical fiber cables. We'll look at those in a minute. Data center cabling is covered by TIA 568 and ISO 11801 through several standards, including ISO 24764, Senelec EN 50173-5, and TIA 942. All standards cover similar topics, offer lots of options for cabling in data centers, and more TLAs, three-letter acronyms, than most standards. Furthermore, as TIA 942 states in the introduction, and I quote, "Data centers are designed to handle the requirements of large quantities of computer and telecommunications equipment. Therefore, telecommunications and information technology professionals and specifiers should be involved in the design of the data center from its inception." From our own analyses of data centers, we believe the approach of traditional structured cabling is not as valuable as it might be in an enterprise LAN. Data centers are highly specialized units where efficiency and modularity are important in the design and consideration for power, cooling, redundancy, and security are often more important than trying to follow some cabling design standard. Most modern data centers have adopted unique cabling architectures appropriate for the way the data center equipment is used. We will look at two designs called top of rack and end of row. You'll often hear about top of rack designs. In this design, the servers are in a rack with the switches that serve them, often at the top, hence the name. This makes the connection between the switch and the servers very short, so less expensive copper cables can be used within the rack, typically UTP or perhaps CX4, Coax standard. This actually limits the copper to each rack as other connections directly to the rack are made on fiber. If the rack connections are limited to 10 gig, this will save money, and there are options for low power 10 gig for short links or copper CX4 that save lots of power. The end of row design has a rack of switches on the end of a row that includes racks of servers. The server racks and switch racks are connected typically by UTP Cat6a for up to 10 gig or fiber for any speed. The switch racks connect to interconnection and SAN switches over fiber optics. End of row racks of switches can be placed in the middle of a row or even used to connect several rows of servers depending on the density of the equipment and the length of separation. Racks will generally have patch panels that allow equipment on the racks to connect over short patch cords so that the large bundle of cables between the racks can be more easily and neatly dressed to connect the servers without creating a mess. Here is a quick summary of data center cabling options. Coax and AOC's active optical cables are used for short links, typically under 5 meters. UTP can be used to its full length for up to 10 gig. Multimode fiber can work over a range of up to 450 meters down to about 100 meters, depending on the speed. Singlemode fiber is becoming more popular because it offers the usual fiber advantages, basically unlimited bandwidth and distance. The cost issue always comes up in discussions of media choice. UTP is usually cheaper but consumes more power. And multimode fiber allows for cheaper transceivers but more expensive cabling than single mode. There's a new option up there, Cat8. It's intended for short lengths and will consume lots of power. Somebody will probably find a way to make UTP work at 100 gig too, but who knows when and how much power it's going to consume. This is a CX4 cable for 10 gig, which uses 4 small coaxial cables. It's good for short lengths, but it requires a special SFP small form factor pluggable module interface for the switch. Category 6A unshielded twisted pair works with 10 gig Ethernet. It's relatively cheap, but consumes about 5 times as much power as a fiber link. It also will require much more space and cable trays on the front of the racks to connect the switches or servers, or under the floor. In category 6A at 10 gig, you have to worry about alien crosstalk from cable to cable. Active optical cables use multimode parallel optics with a permanently attached transceiver. They plug into the receptacles on the switches or the servers that use small form factor pluggable receptacles. They are very useful for short lengths, allow you to use fiber without having to worry about termination. Multimode fiber has become widely used for up to 10 gig. VCSEL laser sources are cheap, use very little power, and multimode fiber is easy to install. But multimode fiber is running out of bandwidth at 100 gig, even OM4 grade multimode. So 40 gig uses 4 different parallel channels of 10 gig transmission, and 100 gig is currently using 10 gig channels. As you can see later, this will have a major impact on the fiber count needed to support the equipment. Both multimode and single mode fiber typically use LC connectors for single fiber connectors because they are the connectors used in transceivers. Parallel optics for 40 and 100 gig use the MPO connector shown in the bottom of the slide. Here are examples of 40 gig and 100 gig solutions on multimode fiber. 40 gig uses 4 channels each at 10 gig for transmit and receive on separate fibers. So there are 4 transmit and 4 receive fibers. Since the MPO connector has 12 fibers, the center 4 fibers are unused. 100 gig uses 10 channels each at 10 gig for transmit and receive on separate fibers on a 24-pin connectors. So there are 10 transmit and 10 receive fibers. Since the MPO connector has 12 fibers in each row, the center 4 are unused. There is a version of 100 gig being developed for multimode that uses 4 25 gig channels, which is expected to have a shorter reach than the 10 channels. The design should use a connection scheme like 40 gig on the 12 fiber connector. Multimode transceivers use inexpensive 850 nanometer VCSELs, so transmitters are cheaper, but the cable plant, which uses so many multimode fibers, is more expensive. Single-mode fiber has practically unlimited bandwidth and distance capability when used in data centers. Unlike the parallel 10 gig channels used with multimode fiber, single-mode fiber uses coarse wavelength division multiplexing to transmit multiple channels over one pair of fibers at different wavelengths. Thus, 100 gig is achieved using 4 25 gig wavelengths over only 2 fibers, greatly simplifying fiber installation and management. These wavelength division transceivers cost more than parallel multimode transceivers at the current time, but the cabling cost is much lower, and the price of transceivers is going down. So what's the best choice for 40 gig or 100 gig? Besides the difference in cost or numbers of fibers to manage, there's an issue with power and loss budgets. The multimode link can only handle about 2 dB of loss, which can be a problem with multiple interconnections with MPO connectors because they have higher loss than typical single fiber connectors. The single mode fiber, however, has no problem with its power budget. Discussions with big data center owners and contractors installing their cabling indicate a preference for going to single mode. It's hard to know where to start talking about cables and installation, as everyone has an opinion and every data center is different. Some data centers use cable trays above the racks, and others place cables under raised floors. In the racks, the cables are probably going to be distribution type cables, but under the floor they may be armored to protect against crush from other cables. Micro cables blown into ducts have been used, as have blown-in fibers. If you choose a parallel optic system, it will be a prefab system, and you will negotiate with the cable choice with the vendor. The type of cables used may be dictated by the design configuration chosen, so the data center designer needs to work with vendors to review options before making a choice. Field termination in a data center can be a big project with so many connections. So many users look to prefab cable plants, or pre-terminated cables, as some manufacturers call them. The good news is they're quick to install. But the cable plant must be carefully designed so it's not too long, requiring storage of excess cable, or not too short, with the obvious bad consequences. You have to add patch cords to make your length. Prefab cabling can be more costly than field termination. MPO connectors have higher loss than LCs or SCs, so you have to watch your power budgets. These connections are very sensitive to dirt, must be carefully cleaned, and special microscopes are needed to inspect them. Whenever one is installing pre-terminated cables, one must have the protective covers over the connectors all the time during installation to prevent damage. Damaged cables will probably need to be removed and replaced, and a new cable may take weeks to get delivered. If the system is prefab with LC modules, as shown here, testing is straightforward. But if you're installing parallel optics with MPO connectors, testing is more complicated. We're actually working on a page on our website and a video just on testing these parallel connections. Single mode and multimode fibers have different problems when used in data centers. Multimode links have bandwidth distance limitations due to modal dispersion. The derating factors for dispersion on multimode fiber can limit power budgets to as low as 2 dB, not the 5 to 6 dB you would figure from looking at the transmitter output and receiver input levels. Single mode links are capable of longer runs, so loss is not an issue, unless the loss is too low and attenuators are needed at the single mode receivers because of overloading. Connector reflectance can be a problem. Reflectance should be as low as possible perhaps justifying the use of APC connectors as are used in fiber to the home and other short-length multimode systems. There have also been stories about multipath interference caused by reflectance and multimoding caused by bend-insensitive multimode fiber on short links, and that can be cured by simply putting a small loop in the suspect cable to strip off the extra modes and see if that solves the problem. We couldn't cover everything we need to cover on cabling for data centers in this short presentation, so there will be others on the topic coming up on the FOA YouTube channel in the near future. Watch particularly for a couple of videos on parallel cabling systems, how to design them and how to test them. We're the Fiber Optic Association, the International Professional Society of Fiber Optics. Be sure to go to our website and check out all the technical information that's available there for free, as well as all of our other YouTube videos.